Our galaxy is just one of billions of galaxies scattered throughout the larger universe. Beyond these galaxies, we can detect the faint glimmers of celestial objects so powerfully energetic, we cannot fully explain their existence. Most of the universe lies so far away from us that we cannot image its details. Yet, from bits of light from these distant celestial objects, we're able to unlock the secrets of what the universe is made of, how vast it might be, and how it came to be as we see it today.
Astronomy is in a very special time right now. Ever since the caveman, people have wondered sort of, who am I and where do I come from? And in the past 20 or 30 years, we're actually getting answers to those questions. We know approximately how old the universe is. We know how the universe began. We know where the individual atoms in our body were originally cooked. These are not speculations now. We understand these things, and we are the first generation that has done so. When my father went to school, we couldn't answer those questions. Now we can. And I think that most people appreciate that's really neat.
People enjoy being first and making a discovery, but almost as much, and sometimes more, we enjoy the surprise. And one of the great aspects of astronomy, at least in the latter half of the 20th century, has been the huge number of surprises that it has provided. In part because of the instruments we've sent into space. It's been like a fish crawling out of water or out of mud and seeing the sky for the first time. There are wavelengths that we could never view the heavens in before. Microwaves, radio, X-ray, gamma ray. And with each of these new horizons has come new discoveries that has been very exciting.
What excites me about astronomy is the doing of astronomy. If you've noticed, in every observatory in the world, there's a catwalk around the dome. You know, why do they put that there? I'll tell you why they put that there. Because an astronomer goes out in the middle of the night and walks around ostensibly to see, are there any clouds coming in, how are things going? But it's the awe. You'll see the summer Milky Way above you. It's just absolutely inspiring. It's beautiful, and the sense of depth is just unbelievable. Of course, you look through your telescope, but you also look at the sky. And many, many times I've been struck by that. There are times I have walked the catwalk like a captain walking the bridge of a ship, and you hold on to the rail because it's almost like you're going to fall up into it. There's just such a sense of depth.
To an astronomer, it's really sad to see that for most people, the stars are on the endangered list. Many people grow up and spend their whole lives in cities and never see a wonderful country starry sky. Never see the Milky Way, never see the beautiful night sky with its myriad stars. And that is a sad loss.
As a child, I looked at the stars in the sky and couldn't imagine at all why those things were there. And even now, when I'm at a telescope on a very dark night and look at the sky, I wonder how anybody could not be an astronomer. How you could find yourself in this universe and not hope to devote your life to finding out what it's all about.
Our fascination and awe with the heavens is not new. Ancient astronomical monuments are scattered throughout the world. The early Greeks were perhaps the first to study the skies in a scientific way. And when that style of inquiry was rediscovered in the Renaissance, the heavens began to take a new shape. Each observation, discovery, and theory built on the ones that came before. Each changed our perception of not just the heavens, but ourselves. We learned that we're not at the center of the universe, but inhabitants of just one planet in a solar system of 9 planets. each with a geography, a geology, and a past that began an estimated 5 billion years ago in a swirling nebula of gas and dust. Today, at the center of this system, is an average middle-aged star only 5 billion years old, with at least another 5 to glow. Revolving closest to the sun is tiny Mercury, covered with craters and looking as desolate as our moon. Next out is Venus, where a deadly cauldron of sulfuric acid clouds and carbon dioxide perpetually enshrouds a rocky, lifeless world. The third planet out is Earth, 93 million miles from the sun, a distance we call 1 astronomical unit. It's the only planet in the solar system with liquid water on its surface, the only one with an oxygen-rich atmosphere, the only one we know of that supports life. Circling the Earth is the Moon, small, airless like Mercury, and covered with craters that give evidence of a bygone epoch. The Moon appears in the sky as large as the Sun, yet it's only 1/4 the diameter of the Earth, a coincidence that can have a spectacular effect. Next out at 1.5 astronomical units from the Sun is Mars. Once upon a time, Mars was teeming with life and an advanced civilization that dug canals and even invaded Earth. Today, we know that while our imaginations put life on Mars, nature apparently did not. Mars is, however, rich with astounding geological features. Its dead volcano, Olympus Mons, dwarfs Mount Everest, and its long canyon, called Valles Marineris, makes the Grand Canyon look like a gully. Beyond Mars orbits a belt of asteroids, thousands of rocky fragments that range in size from a few centimeters to 1,000 kilometers. Some even have their own tiny moons. Most are boulder-sized, tumbling and revolving in an endless procession around the sun. Beyond the asteroid belt lies Jupiter, the colossus of the solar system. Over 5 astronomical units from the sun, Jupiter has more mass than all the other planets combined. Marked with a red spot 3 times the size of Earth, this planet of liquid and gas sports over a dozen moons. Most of them frozen and forbidding like the planet they orbit. But one of them is so geologically active that its surface changes like the weather. At 10 astronomical units from the sun, orbits the planet with features that through Galileo's primitive telescope looked like ears. Today we know they are rings, hundreds of rings made of billions of icy chunks that make Saturn the most visually stunning planet in the night sky. Like Jupiter, Saturn is surrounded by an entourage of well over a dozen moons. At 20 times our distance from the sun is Uranus, a fallen giant whose poles alternately point to the sun. Circling this world are 11 faint rings and numerous moons. At 30 astronomical units orbits the outermost giant planet, Neptune, accompanied by 8 moons and a wisp of barely visible rings. Despite its serene appearance, great storms rage in Neptune's atmosphere. Averaging 40 astronomical units from the Sun are 2 large pieces of space debris, Pluto and its nearly the same size moon, Charon, locked in a face-to-face dance. From their great distance, the Sun must appear as only a bright star in a perpetually dark and incredibly cold sky. This is the solar system. From our view, it is immense. From the universe, though, it is a small collection of gravitationally bound specks of dust.
How big is the universe? It's this big. It is really, really large.
The universe is an immense and also an extremely empty place.
The universe is vast.
Well, the universe is big.
It's hard to imagine how big the universe is. I'm not sure that I really understood it until I had my students go through an exercise of modeling the solar system.
If the sun is the size of a basketball, the Earth would be a pinhead 100 feet away. Jupiter is a ping pong ball 500 feet away. And Neptune, which is the farthest planet from the sun at the present time, is about the size of a pea, 4/5 of a mile down the street. The distance between the Earth and the sun is an astronomical unit, 93 million miles. It's a distance that would take you 17 years to cover in a jet, moving at 600 miles an hour. Yet light is so fast that it can traverse that distance in 8 minutes. And so what you're seeing when you look at the sun happened 8 minutes ago. And we can use light as a scalar for the universe in general, because without something that fast, it's very hard to understand the actual distances involved.
Just getting from the Earth to Mars, that with current spacecraft technology, that can take months to even years. Getting out of the solar system can take decades. Getting to the nearest star system, even traveling at the speed of light, also takes years.
If you traveled in your automobile, for instance, to the nearest star, you would not get there by the end of your life. You wouldn't get there by the end of the next generation. In fact, you wouldn't get there after thousands of generations if you were traveling at the speed limit.
Even for light, traveling at 186,000 miles or 300,000 kilometers per second, the journey takes an incredibly long time. While light takes only about 8 minutes to travel from the sun to the Earth, it takes over 5 hours before it reaches the outermost planet, and years before it reaches the nearest star.
The nearest star, Proxima Centauri, is 4.5 light years distant, which means that the light from Proxima Centauri we're seeing now was packaged 4.5 years ago, and we're only receiving it at the present time. To scale, if the sun were the size of a grapefruit in Washington, D.C., Proxima Centauri would be a grapefruit in California.
The nearest stars are a few light years away. Our Milky Way galaxy is about 100,000 light years in diameter. That is to say, it would take light 100,000 years starting at one edge of the Milky Way to travel to the other edge of the Milky Way.
Our own galaxy is part of a rather small group. It's called the local group. The total size of the local group is about 3 million light years across. So that when we look out at the so-called Andromeda galaxy, or M31, we're actually looking about 3 million years back in time. That's how long it takes the light to reach us.
If you think of the Milky Way galaxy as a grapefruit, Andromeda, which is the nearest large galaxy, is only 20 grapefruit diameters away. It's another grapefruit, 20 grapefruit away.
The most distant galaxies are billions and billions of light years away. We see them as they were, in fact, billions of years ago, because the light has taken that billions of years to get from them to us as we detect it now.
So the size of the universe is best thought of in terms of the timescales over which light travels. And we can define the whole size of the visible universe from where we are today to the point at which we're seeing the relic radiation from the Big Bang. That's the observable universe.
It is quite probable that the universe has an absolutely enormous size, much larger than the 15 billion light years to which we can directly see using the largest telescopes. It's probable that that part of the universe that we can see, that is the observable universe, is really only a tiny fraction of the entire universe. Much like the part of Earth that you walk on most days is only a tiny fraction of the true surface area of the Earth. This means that we will never really know what's going on in a vast majority of the universe.
The fantastic distances between the objects that populate the universe boggles the mind. Just as astounding, however, are the objects themselves. We once thought that the heavens were changeless, permanent. We now know that the universe is active, even violent. As it's continuously torn on a colossal scale by fundamental physical forces. In the arms of galaxies, we see evidence for a complete cycle of star birth, life, and inevitable death. We see that most stars, after only a few billion years, burn up their nuclear fuel and leave behind a white dwarf, a star no larger than the Earth, yet 1,000,000 times more dense. When a more massive star grows old and becomes a red giant, its core eventually collapses and triggers a supernova. An unimaginably large explosion that can be seen 1 billion light years away. What often remains from these cosmic calamities is a tiny neutron star, so dense that a single tablespoon of its matter would weigh 100 million tons. In some cases, this neutron star spins rapidly, emitting radio signals. If detected on Earth, it's seen as a pulsar. Some of the most massive stars die the strangest deaths of all. Such stars collapse in on themselves, creating matter so dense, with a gravitational pull so great, that nothing can escape, not even light. From these strange places, we can sometimes detect X-rays and observe jets of particles streaming from an unseen source, a black hole. As astounding as these objects are, the universe holds still greater mysteries. At the heart of a giant galaxy such as our own may lurk a supermassive black hole, so powerful its gravity can bind millions of stars. With celestial objects so fantastic at such great distances, how can we even begin to make scientific guesses about their nature? The answer lies in one simple but vital assumption. We assume that the physical laws we observe here on Earth are the same everywhere. That hydrogen, for example, glows in a measurable way, whether it's in a laboratory or in the heavens. That gravity we observe every day is the same kind of gravity that binds the stars to galaxies and galaxies to one another. In short, we assume that the laws of nature are indeed universal, and that by studying it in a systematic way, we can unlock the secrets of the universe.
Number 39 in the reference field has a redshift of 0.4.
Astronomers are a group of people that sees the universe as a system of interacting rules that is understandable. And what we do is try to figure out what the rules are that describe how the universe works.
The exact centering of this star on a given pixel will not be the same. There will be some difference in spacecraft jitter between the two images, which is why you see more of the tendrils here and maybe less of the tendrils there.
The universe provides a kind of laboratory, and it gives samples of what's going on. You know, how do we learn things? Well, we go out and look at things, and we feel them, and we study them, we think about them. Even in the laboratory, it's the same thing. We may look through a microscope, we may test with instruments, but that's basically an extension of our senses. And we try to measure and look and find out things and see what's there.
Astronomy is different from all of the other sciences because astronomy is entirely observational. The chemist can go into his laboratory and experiment on his chemicals. The physicist can build an apparatus and change it and test it. But the astronomer can't go out among the stars and kick a star to see what happens. We can only gather information by looking, and so we have to build telescopes. The telescopes gather photons, photons of light, photons of X-rays, photons of infrared, whatever. They gather photons because that's the only way we can get information about what goes on in the heavens.
Understanding that the laws of physics that have been developed have to be maintained. And what you hope is that you can explain everything using what you see and the laws of physics, but you might have to invent some new physics when you get out there and see the way the whole universe functions.
Astronomy allows us to look at situations that can't be produced on Earth. Completely different situations than anything we can produce in the laboratory here. So it's a laboratory out there dealing with quantities and behavior that we can't possibly duplicate here, and that gives us then a new insight into basic phenomena and what can happen and how the universe itself was built.
The astronomer can probe the laws of physics as they are very far away in the universe, and because the light that carries the information that the astronomer is examining takes a long time to get to us, he or she can actually also probe the laws of physics backwards in time, the way those laws used to be when that light was emitted and began its travel towards us. The astronomer can test the universality of the laws of physics both elsewhere in space and backwards in time.
From the primitive refracting telescope of Galileo to the Hubble Space Telescope, every advance in our knowledge of the heavens has in large part been a reflection of our advances in technology. So that today astronomers have a wide array of tools for collecting the light from above. But it's taken more than machines and devices to pull back the curtain of heaven. We've come to know what we do about the universe from those who have chosen to examine it in a scientific way. Men and women who today continue to be drawn to the stars.
I think each new technological breakthrough brings us a new field of astronomy. And of course, each new technological breakthrough brings us completely new results, introduces new people to the field, and they're all astronomers.
There are many, many questions we would like to answer. Perhaps unlike some of the other sciences, a good astronomer can think of 10 or 20 or 30 questions that he wants to answer at any one time.
How did our Earth form? What are the laws that govern behavior of matter?
Is it worth going out there?
How did these stars get to be the way they are?
How did our galaxy form?
How long does a star take to go through its life cycles?
What is the fundamental nature of the universe? Where does it come from, and where is it going?
Astronomy is the study of these questions. These are the most basic questions that we can ask of ourselves and of our surroundings. Astronomy really is the study of everything in the universe, and as such can be considered the grandest of all subjects, because it is truly all-encompassing.
Anytime there was expansion of humanity across the surface of this planet, there were always scouts. Always somebody went ahead to say, well, is it dangerous out there? Or is it interesting out there? And in a very real sense, astronomers are the scouts for the entire human race, because we've only got one place left to go. We've gone every place on this planet. The only place left to go is out and up.
Why explore the planets, the stars, and all that lies beyond? The reasons for venturing into this infinite frontier, for exploring with our eyes and minds places we may never go, are as varied as our imaginations. But the full answer lies not just within ourselves, but in the stars.
Appears as a dazzling array of lights, a sparkling canvas whose graceful motions mark the passing of time. For centuries, these images have inspired and challenged our imagination, daring us to uncover their secrets and determine our place in the cosmos.
All of the cultures that live on Earth live under the same sky. And all of the cultures that have ever lived on the Earth have lived under the same sky. The sky has not changed significantly in 10,000 years. And that means that every culture deals with the same problems, looking at the sky and trying to understand what it is.
If we really want to comprehend astronomy, we need to comprehend these changes that occur in the sky through the seasons and through the night.
This kind of astronomy that we're talking about is very simple astronomy when it comes down to it. It only takes two things, a place to stand and a place to look.
It is here under a starlit sky where the journey of astronomy began many thousands of years ago. To our most ancient ancestors, the sky provided order and guidance, offering important clues essential for survival.
Astronomy was originally rooted in practical everyday reality. The sky provided the basic means of understanding such things as direction in the landscape. That's where we get things like north, south, east, and west. It also provided the basic rhythms celestially for the passage of time, the regular cycle of day and night, the monthly packaging of the phases of the moon, the annual circuit of the seasons and the stars and the sun. All of these things were tools that people used from deepest antiquity, probably back to the Old Stone Age, in order to help them organize their lives and adapt with wit to the environment in which they found themselves.
People who live in traditional cultures associate the changes they see in the sky with the changes they see in the earth. They know that when certain stars appear in the evening sky, in the early evening, or appear for the very first time in the early morning, that certain trees will bud, that certain animals will have their offspring. So these are all clues that are used for very basic human things, for when to plant, when to harvest, when to hunt, and so on.
Understandably, the people of ancient times watched the sky with fascination. There they saw reflections of themselves and their world.
Wherever we go to look for the signs of ancient astronomy, we'll find astronomical symbolism, the recognition that the sun has power and that the moon measures time and that the stars spell out the course of the seasons. But the forms in which these things evolve varies tremendously. They show up in the symbols, in the ceremonies, in the architecture, and in the myth of all of these peoples, but exactly how they show up depends on the character of the society and the environment they occupied.
We grow up with basically the Greek constellations today. We have, for example, the constellation of Ursa Major, the Great Bear, that contains the 7 bright stars we call the Big Dipper. But my Navajo friends don't call that group of stars the Big Dipper. They call the 7 bright stars and some associated ones nearby the revolving male. They refer to the North Star as the fire star, and they refer to the constellation we call Cassiopeia as the revolving female. And they associate this with being at home around a fire in their hogans and family values.
Chinese constellations are conceived very differently, often shown as little balls representing the stars and sticks connecting them. But the identities of these ball and stick constellations vary tremendously. For example, the Big Dipper is really a celestial chariot or vehicle in which a celestial bureaucrat or the emperor travels as he goes around the North Pole of the sky. Well, we can go around the world and find different interpretations of these different groups of stars.
We have the constellation of Scorpius in the south, a very beautiful summer constellation. It looks like a scorpion. The Pawnees separated it into 2 constellations. The first part, the front part, is a string of stars that they called the snake, and then the stinger of the scorpion they called the swimming ducks, and that set their whole calendar, those 2 stars.
While different cultures projected different images on the sky, one celestial object was regarded by all as the supreme power in the heavens.
You couldn't doubt that the sun had power, for when it came up above the horizon, it glowed. It glowed with intense light and changed the landscape from the darkness of night, which was often seen as a threat to people. In fact, even the underworld might be thought to be loosed at night. And so the sun came back and brought light and life to the world. And of course, you could feel the heat of the sun on your own face. And that was further evidence that there's real power, as there is in the sun.
Many ancient cultures tried to understand the sky, the ancient Babylonians, for example. Most of those cultures approached that understanding in a spiritual way. They saw the sun as a creature, a spirit, a god, moving across the sky day by day, eastward among the stars. Many of those cultures worshiped the sun.
Whether it was Re, the god of the sun for the ancient Egyptians, or Shamash for the Mesopotamians, it often represented very similar principles. The sun also was recognized as having a link to the life of creatures, plants and animals on the earth, because their seasonal changes seem to coincide with the seasonal movements of the sun. So the sun was regarded as a source of order, and we can appeal to ancient Hindu tradition, ancient Egyptian tradition, or ancient Babylonian tradition, and we'll find those same themes repeated.
Many of them feared the sun, and a great many of them feared that when the sun moved toward the south, getting closer and closer to the winter solstice, that the sun would not stop. The sun would continue going southward, it would disappear, and the world would perish.
In time, you see people investing symbolic meaning with the sky, and they take that symbolic meaning, which is a reflection of the things that are important to them in their own lives, and they incorporate it into their sacred places.
At Stonehenge, one can stand at the center of that huge monument using very massive stones that have been transported for very long distances. At Stonehenge, we have one outstanding astronomical alignment. It's called the heel stone that you see from the center of Stonehenge, and at the summer solstice time, the sun is rising directly over the heel stone. Well, that probably is not accidental. That is an observation that was made into Stonehenge.
Stonehenge, in a sense, while maybe unique, is hardly alone. There are 900 stone rings in Britain alone, and those are just the ones that are left. And there are other kinds of monuments besides these stone circles that also are very good candidates for astronomical alignment.
There's the Bighorn Medicine Wheel in northern Wyoming, for example. That also has a summer solstice sunrise alignment, a very definite one. In that case, that's a monument made from small stones, many of them being piled up in what looks like a wagon wheel kind of pattern. It apparently has some of these heliacal risings of stars that predate and follow the summer solstice that are built into it as well.
Now, of course, the question is, who built it and what did they use it for? You begin to wonder, are we dealing again with an attempt to make astronomical observations? Are all these structures the same? What exactly is going on? And of course, the real answer is, we just don't know. Each one is a product of the culture that built it. In part, it has to do with a concept of religion that is related to what people might call a showing of the sacred. The sun or the stars or the moon or whatever they might be, representing as they do powerful cosmic forces that move and order the world, make their presence known at key times and in key places, and in turn make those places sacred. And so whoever's there, the pharaoh, the king, the priest, whatever it might be, that person becomes a participant at this right place, at this right time, for this showing of the sacred that kind of puts the cosmic good housekeeping seal of approval on that society's activity.
Ancient cultures grounded their astronomy in myth and legend and built great monuments to support their beliefs, until the arrival of a civilization that brought a new perspective to the images of the sky.
Certainly something very interesting happened in the Mediterranean at the time of the Greeks. Greek science is something that we can clearly see the roots of modern science in. And it has to do with this sense of modeling the universe mathematically, being able to predict what might happen next, and being able to test and reject ideas on the basis of rational thinking. That kind of approach, kind of a skeptical approach to nature, isn't the sort of thing that we would necessarily find in any of the sacred kingdoms that depended on a mythological worldview.
With their new worldview, Greek astronomers analyzed and categorized the sky based not on myth, but on objective observation.
One of the things that we notice when we go out at night, whether we're astronomers or not, is that stars have different brightnesses. They're faint stars, they're bright stars. The first person to use the term magnitude in an astronomical sense was Hipparchus. He divided the bright stars up into 6 groups. Group 1 was the brightest stars, Group 6 was the faintest stars. These magnitudes that Hipparchus set up were obviously visual magnitudes. They're magnitudes as we see them with the eye, and the average eye is always the same. Now, of course, when we got telescopes, we could see stars fainter. And so we have to apply magnitudes to those stars. And so the magnitude scale goes from 6 down to 10, down to 15, down to 20, and so forth. The larger the number, unfortunately, the fainter the star is.
The Hipparchus magnitude scale is somewhat inconvenient for use today, and that is due to the fact that the scale is pretty much upside down. The bigger the number, the fainter the star. It becomes a little more inconvenient when we have to look at objects that are brighter than the stars. For example, take a look at the planet Venus. In the Hipparchus magnitude scale, Venus would have a magnitude of -3 or -4. In other words, for objects brighter than the brightest stars that Hipparchus could see, we have to use negative numbers. And the moon would even end up being a -11 on this scale.
The Greeks struggled to explain this awesome spectacle of lights with their newly conceived scientific methods.
But the ancient Greeks did something that, so far as we know, no one had ever done before. They tried to build models. They tried to build actual physical descriptions of what the universe was like. Nobody had done that before. Living on the Earth, it's really hard to understand what the universe is like. When we look at the sky, it looks like a great plaster dome overhead with the stars stuck on like thumbtacks. And in fact, that's the way the Greeks thought the universe really was. And they created the idea of a celestial sphere, a globe that completely surrounded the Earth, and the stars were stuck on the globe like thumbtacks in the ceiling. We know that's wrong now. We know that the stars lie at all different distances from the Earth. Some are very far away, and some of them are really quite close. But still, the celestial globe is a useful model.
Using the concept of a celestial sphere, the Greeks described what appeared to be a sky in motion.
It doesn't take very long before one notices that the night sky changes over a period of time. We notice that these constellations, as a group, move across the sky from east to west. We get the impression that the sky is literally turning above us. On Earth, we don't feel the Earth moving at all. Therefore, the logical conclusion was, and this was made by the ancients, and just about all ancient civilizations made this conclusion, was that the celestial sphere, the giant sphere of the heavens with the stars imprinted upon it, was moving, was rotating slowly, recreating that daily motion, the rising of the stars in the east and the setting of the stars in the west.
Using the celestial sphere, the Greeks defined the two most important lines on the sky, the celestial equator and the ecliptic.
The celestial sphere has a globe of the Earth in the center, and the rotation of the Earth on its axis defines the north and south pole on the sky, and it defines the celestial equator. The celestial equator is the line around the heavens exactly above the Earth's equator. That line divides the heavens into a northern hemisphere and a southern hemisphere. We can see that that line is defined by the rotation of the Earth. The Earth has another motion. The Earth revolves around the sun in an orbit, and that defines a line on the sky.
This path that the sun seems to follow over the course of the year as a result of the Earth's motion around the sun is called the ecliptic. If we could see constellations behind the sun, then we would notice that the position of the sun relative to those background constellations is changing as the Earth orbits. Its name probably originated from the fact that this was the zone in the sky in which eclipses occurred, hence the name ecliptic.
While the Greeks gave us a new perspective on the sky, the motions they described were more than mere celestial phenomena. They were cycles that, in fact, ruled life on Earth. On this planet, we live within two major cycles, both determined by the apparent motion of the sun.
The sun, after all, does some things pretty much the same for everybody. It orders the world. It comes up every day and goes down every day and brings light to the world. And then over the course of the year, it follows a pattern that establishes direction in the landscape and also consolidates the calendar into a repetitive cycle. It changes the height of its crossing through the course of the year. This was linked in turn to the weather, and the seasonal change obviously modulated the behavior, not just of the rest of the animals and the plants, but of people themselves. Well, that is power, and people were right to recognize that power. They attributed to it a divine source, whereas we today, of course, recognize it as physical.
The Earth rotates on its axis in 24 hours, and that makes the sun rise and the sun set, and that produces our cycle of day and night. Our bodies are tuned to that cycle, and we awake and we sleep with that cycle.
Proof of the Earth's daily motion can be seen in a Foucault pendulum. As the pendulum swings, the plane of its motion defines a fixed direction in space. Since we know inertia prevents a change in that direction, the pendulum's observed motion around the room must be caused by the daily cycle of the Earth's rotation.
The other cycle is the orbital motion of the Earth around the sun. The Earth travels around the sun in 1 year. The Earth goes through seasons, and we live within that cycle too. We're creatures of those two cycles determined by the two motions of the Earth.
Traditional people noticed this. They didn't explain it as we do, of course, today. They thought of the sun as moving around us every day. They thought of the sun as usually as a deity of some sort. Certainly they knew that it was essential to their very existence. And this change that occurred throughout the year, every single year, was very, very important, very fundamental.
If we were to keep track of the motion of the sun in the sky over the course of an entire year, we would discover that the sun does not rise at the exact same point in the east every day. In the month of June, the sun rises far to the north of the east, and from a northern hemisphere view, the sun reaches its highest point in the sky along its ecliptic path. And we define that point as the summer solstice. It would correlate to the longest day of the year in the northern hemisphere.
The solstices and equinoxes around the ecliptic are marked on our calendars today as the beginning of the seasons. Many cultures celebrated those with holidays. The summer solstice was often celebrated as the beginning of the summer season, the beginning of the intense growing season.
Towards the end of September, September 20th, 21st, we would reach a point where the sun would rise due east. It is at this point that the sun, along its path, crosses the celestial equator. The length of day and the length of night would be equal in time, and we have the equinox.
Autumnal equinox in September was often celebrated as the harvest season. It was a time when the harvest was gathered and the fruits of the summer's work were brought in.
Finally, in December, around December 20th, 21st, we would notice that the sun would rise far to the south of east. As it moved across the sky, we would discover that it would be very low in the sky for northern hemisphere observers. The days would be short. And as a result, we would have a day called the winter solstice.
The winter solstice was often celebrated too. It fell at a time when people couldn't farm, and they would celebrate that solstice as the midpoint of the winter season. So many cultures had ceremonies, prayers, celebrations to appease the sun and to call the sun back into the northern sky so that spring would come and the earth would come back to life.
As the year progresses, the sun continues its journey along the ecliptic path, finally reaching a point in March, around March 20th, 21st, again a point where the sun would rise due east, crossing the celestial equator. We would have again equal length of night and day, we would have the spring equinox. And the cycle continues.
To the people of ancient and traditional cultures, the seasons were caused by the annual migration of the sun. Today, we know the real cause is much closer to home.
We have seasons on the Earth because the Earth's axis of rotation is tilted away from the perpendicular to its orbit. The Earth is tipped slightly toward the sun, and you can see that the sun is north of the Earth's equator. And from the United States, the sun will cross high in the sky, we'll have warm weather, and it'll be summer. Now in 6 months, the Earth will revolve around to the other side of the sun, but notice the axis of the Earth is still pointed in the same direction. The sun is south of the Earth's equator. And that means that through the day, the sun doesn't come very high in our sky in the United States. We don't get very much heat from the sun, and so winter days are cold.
Just as the motion of the Earth changes our perspective of the sun, it also changes our view of the nighttime sky.
If we set up an observing schedule and go out and look at the night sky, say at 9 o'clock every night for days and weeks and months, we discover that the groups of constellations change. In other words, during the winter months, we would be able to observe the constellations of Orion and Taurus and Gemini. And yet, if we were to do the same observations at the same time, 6 months later, we would observe the constellations of Hercules and Sagittarius and Scorpio. This led the ancients to believe that there was a yearly cycle to the motion of the sky, in addition to the daily motion of the rising of the stars in the east and the setting of the stars in the west.
By carefully watching this yearly cycle of stars, the ancient Egyptians discovered another earthly motion, one so subtle it was detected only over hundreds of years.
They built temples that were aimed at the rising point of important stars like Sirius, and they noticed that after a century or two, Sirius wasn't rising in the same place anymore. So they had to modify their temple and twist the hallways to make them point toward the right spot. They saw precession.
Precession is the phenomenon that occurs when a spinning top wobbles on its axis of rotation. The Earth does the same thing. It's wobbling. Due to the gravitational effects of the sun and the moon, this axis of rotation is slowly tracing out a circle in the sky. It's moving, not tipping over, but wobbling very slowly. In fact, it takes approximately 26,000 years for the Earth to make one complete wobble on its axis.
That precession has even changed the North Star. Thousands of years ago, when the ancient Egyptians were looking at the sky, they didn't see the same North Star that we see. The North Celestial Pole pointed toward a different star. And in a few thousand years from now, our descendants will no longer have a star near the North Celestial Pole. We can actually detect precession with telescopes rather quickly. In a matter of months, you can tell with an accurate telescope that the stars are not quite in exactly the same position that they were just a short time ago. So precession is a continuing process, but it takes a long time to go through one complete cycle.
From an Earth in motion, the sky presents a magnificent ballet of lights, an elegant dance that has gone on for thousands of years. Today, through science, we understand the sky more clearly, and still it fills us with a sense of mystery.
There's a favorite poem of mine that comes from the Algonquin Indians. These are Indians that lived in the eastern part of the U.S., woodland Indians, that expresses the sky in a very beautiful way. We are the stars which sing. We sing with our light. We are the birds of fire. We fly over the sky. Our light is a voice. This is the song of the stars. People throughout time and in different places have, so to speak, listened the song of the stars in ways that made sense to them in their time. Astronomers today do the same thing. You could say that they too are listening maybe more accurately and more detailed to the Song of the Stars, trying to understand the words and the phrases, trying to get more out of the energy, out of the voice of the star, if you will, that comes so far across space to reach us.
What they are, within our view each night, yet seemingly forever beyond our grasp. As recently as the last century, we assumed that because the stars are so distant, we could never truly know anything about them beyond their silent twinkling in the night sky. Not what they are, how large, nor even how far away.
Astronomy is different from all of the other sciences because astronomy is entirely observational. The chemist can go into his laboratory and experiment on his chemicals. The physicist can build an apparatus and change it and test it. But the astronomer can't go out among the stars and kick a star to see what happens. We can only gather information by looking.
Any information we have about distances to objects in the universe are built on a firm foundation of knowing how close the nearest stars are. To do any kind of astronomy at all, you have to do intercomparisons of objects, and the only meaningful way you can do that is if you know how far away they are.
The furthest star is so far away that we can't even see that it's spherical in size. It could be cubical, or it could be a pyramid, or it could have advertising written on the side. All stars look like unresolvable specks of light.
So little to go on. Tiny points of light at unimaginable distances. Yet, by learning to precisely measure these heavenly glimmers, we've unlocked the secret of how stars work. The ancient Greeks were the first to note the precise locations of stars in the night sky. While they could only wonder about the distances to this panoply of lights, today we carry on this tradition in the field of astrometry.
In the simplest terms, astrometry is the measurement of the position of stars. It may be planets, it could be the sun, but it's the measurement of the positions of stellar celestial objects. And it's important because objects move, and from the movement of objects we can determine many things. One of the most important would be the parallax of stars.
Well, the way I like to explain it is, and to illustrate the effect is just do the simple sort of thing of holding your thumb up in front of your face. If you do that and you look at your thumb and you blink your eyes, one eye and then the other one, your thumb appears to jump back and forth compared to the background. If you do that with your thumb very close to your face, it'll jump back and forth over a large arc. If you do it when your thumb is farther away, blink your eyes again, it'll jump back and forth, but not with as large a jump. That's the effect we're looking at in trying to measure parallax.
Now, can you use this to measure distances of stars? It'll be nice to pluck your eyes out and stick them millions of miles apart, And then if a finger was very, very far away indeed, you could still see the shift back and forth. But we don't do that. But what we do is take a picture of a section of the sky, say in June, and take a picture of that same section of the sky in December and compare the positions of stars.
Once a star's parallax is determined, its distance from the Earth can be calculated using principles of triangulation.
For example, surveyors who can't get across the river would lay out a baseline on one side of a river, and from one end of the baseline site a point on the other side, and then from the other end site the same point, and the angles between them, they could then use trigonometry to solve the distance across the river.
It's sort of equivalent to blinking one eye and then the other eye, and then the star that we're interested in that's nearby, sort of like your thumb, will jump back and forth compared to the distant background. The bigger the motion, the nearer the star, and we can then calculate its distance.
The determination of stellar parallax is almost as old as organized astronomy itself. It dates from Greek times. If indeed the Earth moved around the sun as many, like Aristarchus, speculated, then the stars should show parallax. But no parallax was found.
On measuring parallaxes, it's easy to point out why the early astronomers could not measure the parallax even to the nearest star. The angle of the parallax of the nearest star is less than a second of arc.
Parallaxes are measured in angular units as arc seconds, and 1 arc second actually is a terribly tiny angle. As an example, if you think of a dime, you hold up a dime or have a friend hold up a dime and then walk off about 2 miles away from you. Then when you look at that dime, you're looking at an angle of about 1 arc second. So 1 dime at about 2 miles is an arc second. There are no parallaxes that are that large. The nearest one, Proxima Centauri, is about 3/4 of an arc second, and everything else is smaller.
Stellar parallaxes were finally found when astronomical technique had become refined enough to measure very, very precisely the positions of stars. And in fact, in the early 19th century, in the 1830s, 3 techniques independently were brought to bear to determine parallaxes of 3 different stars by 3 different astronomers.
They measured by standard clock and eye techniques. Laborious, hard-going work. Probably 20 parallaxes were known up until the 1900s, when astronomers introduced photographic plates and measurements. Then, with the introduction of photographic measurements, we could measure smaller displacements and therefore many more parallaxes.
In this century, astronomers have continued their observations with ever more sophisticated technology.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
We have a beautiful shot of those Viking edges.
In the late 1980s, the European Space Agency launched its Hipparcos satellite to make the most precise stellar measurements to date, far above the Earth's turbulent atmosphere. Over a period of several years, Hipparcos gathered data on the positions, distances, and velocities of more than 100,000 stars. Other researchers are now building upon Hipparcos's data.
We have another study that we're doing with the Hubble Space Telescope, and this is an attempt to tie one particular data set to another particular data set. And the one data set is the wonderful astrometry being done by the Hipparcos satellite. Now the problem is they need to nail that reference system down. And the only way you can do that is by relating the stars, all of these stars that they're studying are stars in our galaxy, and we live in a rotating galaxy. So there's some motion of the entire sky, in a sense. Hubble Space Telescope's use in astrometry works this way. The telescope has 3 fine guidance sensors. 2 of these fine guidance sensors are used to hold the telescope in place. When we move Hubble Space Telescope around from target to target, in order to keep it locked on a target, we use 2 stars. So while we hold the telescope with 2 of these fine guidance sensors, the third is able to walk through a certain field of view measuring positions of stars. So we'll measure stars that Hipparcos has measured, and we'll measure quasi-stellar objects at the same time, and we'll link those 2 systems together. And basically it puts a brake on the rotation of this wonderful reference frame that Hipparcos is coming up with.
Measuring the distances to stars continues as one of astrometry's key tasks. Through astrometry, we now realize that even the nearest stars are several 100,000 times farther than the Sun. This revelation was a vital link in our understanding of these celestial specks of light. Under the canopy of the evening sky, the heavens present an expansive array of lights, each differing in intensity, from faint glimmer to radiant glow. These differences in brightness held our next clue to understanding the stars.
This range in brightness was so obvious to everybody throughout history that even in ancient times, the Greeks, as they began to use the first star catalogs, felt that they wanted to include in the catalog not only the name of the star and its location in the sky, but also some kind of an indication of the star's brightness. And so a Greek astronomer named Hipparchus came up with the first brightness scale, which we call the magnitude system today.
These magnitudes that Hipparchus set up were obviously visual magnitudes. They're magnitudes as we see them with the eye. Now, of course, when we got telescopes, we could see stars fainter. In fact, that was one of Galileo's proofs that the universe was larger than we thought it was. He could see fainter and fainter stars.
The original scale was no longer useful, and at the same time they didn't want to abandon it. I know that many modern astronomy students would have been happier if they had just dropped it and started with something more sensible from scratch. And so 150 years ago, astronomers decided simply to modify the ancient scale and otherwise continue to use it today. In order to modify it and make it truly numerical, they had to decide what exactly does a magnitude mean. It turned out that one magnitude had to correspond to a factor of about 2.5 times in brightness. A first magnitude star would be 2.5 times brighter than a second. A second is 2.5 times brighter than a third 2.5 times brighter than a fourth, and so on. Not only does this allow us to express fractions of a magnitude now, we could say a star is 1.76 magnitude, if that's what it is, but we can also extend the range or the scale beyond the original range of 1 to 6.
Even after astronomers modified the ancient magnitude scale, it could still only tell us how bright a star appeared to be. What we really wanted to know was the true brightness of a star, or its luminosity.
Unfortunately, there's no way to measure the luminosity of a star directly. When you aim a telescope at a star, no matter how precise the instrument is that measures the brightness, all you can measure is the light which actually reaches you.
Now, to fairly compare stars, the energy that stars give off, their magnitude, we have to put them all at the same distance. So again, we need to know a little bit about the distances to stars.
Fortunately, there's kind of a loophole here that astronomers can take advantage of, and that's the fact that light behaves in a very simple as well as a very predictable manner. If you move twice as far away from a star, it becomes 4 times fainter looking. 2 squared is 4, you square the distance. And so because light behaves predictably like this, if you were to measure the apparent brightness of a star, which is what apparent magnitude expresses, and if you were also as a separate step to somehow determine the distance to the star, using, for example, the parallax technique, then it would be possible, knowing how light behaves, to actually calculate how luminous the star must be. In other words, how much energy is that star generating every second in order to appear as bright as it does at that particular distance. When astronomers made these measurements or calculations for the first time, they were really surprised by how much of a range there was even in the true brightness of stars, in their luminosities. They were expecting that stars were all very similar and that their different appearance in the sky was simply a result of them being at different distances. Distances certainly have a lot to do with it, but even luminosity varies over a surprisingly large range. We have measured, detected stars that are as much as 1 million times more luminous than the sun. That's their actual energy output now. That means that they are producing 1 million times more energy every second than our sun is. And there are also some stars that we've found that are as much as 10,000 times less luminous than the sun, producing 10,000 times less energy every second. And this is a fact that we have to accept. That is, any theory that we put forth to explain how stars work has to be able to account for this tremendous range in energy output.
By comparing such properties as distance and luminosity, we had for the first time clear scientific evidence that the sun is just a very close star. But we had yet to learn why there were such great differences between these distant suns. Since stars are suns, we know they must be intensely hot. Measuring just how hot the surface of a star is was our next step in understanding how stars work.
When astronomers first started taking spectra of stars, they spread the light out into the rainbow and they noticed a certain pattern of dark lines in the spectra. They didn't know what the lines meant. They didn't know why they varied from one star to another. The reason for the difference in the appearance is almost entirely due to differences in temperature. That in very hot stars we will see a certain set of lines, helium happens to be one. In cool stars we will see a different set of lines.
The temperatures of stars can be determined quite exactly by seeing how bright stars are in different colors, different wavelengths. So, for example, I could put a filter in front of my telescope which allowed me to observe only the blue light, and then another one that allowed me to observe only the yellow light, and a third that allowed me to observe only the red light. And just by intercomparing those three colors, I would be able to, in a quite straightforward way, determine the star's temperature.
It's clear then that the colors have something to do with temperature. And there's a very nice little example of that. If we watch a filament of a light bulb warm up, if we turn the light on with a rheostat very gradually, we see the filament come on as a red filament. That's because it's relatively cool. And as we put more energy through that filament and get it hotter and hotter, as it heats up, it gets sort of yellow, then it gets blue. So we can see immediately that the color of a star is a measure of its temperature.
Most of the common stars that we see have temperatures in the range of maybe a few thousand degrees to up to 50,000 degrees, although we know the range of temperatures of stars is much larger than that. But typical a star like the sun has a temperature of about 6,000 degrees. So the range is from a few thousand to a few tens of thousand for stars that you and I are familiar with. There are very peculiar or faint stars that may be much cooler and stars that are much hotter, but they're rare.
Near the beginning of this century, a couple of astronomers named Hertzsprung and Russell began to compare stars and their characteristics. They created a type of diagram, which we call the Hertzsprung-Russell, or simply the HR diagram in their honor today.
The HR diagram stands for its two independent co-discoverers, the Hertzsprung and the Russell diagrams, which only came together as the HR diagram in the 1930s.
Basically, they took advantage of the fact that by that point in history, astronomers had measured surface temperatures and luminosities for a great number of stars in the sky. So they felt it was about time that we compared those two characteristics to see if, in fact, there is any kind of a relationship, if the temperature of a star has anything at all to do with how luminous that star happens to be.
Einar Hertzsprung and Henry Norris Russell were trying to appreciate ways to describe how stars varied in their physical characteristics of brightness, spectrum, color, and used these graphical relationships to express their ideas.
And so in this diagram, in which temperature and luminosity are compared, temperature is explained or described horizontally. That is, the farther a star is to the left on the diagram, the hotter and bluer the star is, and the farther the star is to the right on the diagram, the cooler and redder it is. One of the ways that we have to determine the surface temperature of a star is by studying its spectrum and determining its spectral class. And so many of these diagrams have those famous 7 letters, O, B, A, F, G, K, M, which indicate the temperatures ultimately of the stars, going from hot to cold. In addition, the luminosity, or intrinsic brightness of the star, was expressed vertically on this diagram, with the brightest stars at the top and the faintest stars at the bottom. So every star, at any given moment in its life, has a particular temperature, particular luminosity that can be measured, and so every star up there has a particular location on this diagram if we were to choose to plot it on this diagram. This is not a plot of a star's position in the sky, rather it's a plot of its characteristics at that particular moment in its life.
Astronomers discovered that about 90% of observable stars fell along the diagonal line known as the main sequence. For these stars, it could be clearly seen. The hotter they are, the brighter they are.
There were, however, some stars that appeared at first to be an exception. There were some stars in the upper right part of the diagram which managed to be extremely bright despite the fact that they were cool and reddish in temperature.
Off the main sequence, astronomers discovered that these were giant and supergiant stars, cool stars made bright by their tremendous size. They also discovered white dwarfs, intensely hot yet faint because of their tiny size. Closer yet to understanding stars, the HR diagram showed us that a star's temperature and luminosity are directly related. However, it could not in itself explain why. To solve the final mystery of why stars vary so much in brightness and temperature, we needed to actually measure their diameters and masses. For that, we looked to binary stars.
Just before the discovery of parallax, astronomers studying pairs of stars, stars that appeared to be close to each other, just by chance, found that one star was moving around its bright neighbor star. The astronomers realized immediately, this was William Herschel, realized immediately that this was a manifestation of Isaac Newton's laws of motion, that the second star was tumbling around the first, just as the Earth falls around the sun. And once we can determine where the center of mass is and what the distance is to that center of mass, we can determine all the orbital parameters and the masses of those stars.
It turns out that if you have two stars going around each other, and you know how far apart they are, and you can measure how fast they're moving, basically how long it takes to complete one orbit, well, the faster the stars are moving at any given distance, the more gravity there has to be in order to keep them in orbit, to keep them from flying off into space. But the more gravity there is, the more mass there must be as well.
Well, the first binary stars are visual ones in which a person looked through a telescope and saw two stars there. And if they happen to be relatively close to the solar system, and they were patient enough, then from year to year they saw the positions of these two stars change. And eventually, if they watched them, then they could detect that the periods are 10 years or 100 years or something like that.
We can measure how long it takes to complete one orbit. We can compare that to the law of gravity and calculate the masses involved, as long as we understand that it's the total mass, the mass of the two stars combined, that we're actually measuring here. If we want to go one step further and decide how much mass goes with one star and how much goes with the other, we have to remember that the two stars are orbiting around a common center of mass. That's the point that stays still while the two stars go around it. And that center of mass is proportionately closer to the more massive star. If one star is 3 times more massive than the other, the center of mass is 3 times closer to it.
Very often the two stars will be so far away that through a large telescope they look like a single spot of light. But if you look at the spectrum, you'll see that the absorption lines in the spectrum move back and forth. If you measure their wavelength on one night, it will not be the same as the wavelength on another night. What causes that is the Doppler shift. As one star rotates around another, it'll alternately be coming towards you or moving away from you. When it comes towards you, the spectrum is shifted towards the blue end of the spectrum, and when it moves away from you, the spectrum is shifted towards the red end of the spectrum, so that you see a regular change in the wavelengths of the spectral lines. And that's the key to the presence of a binary star.
Among the binary stars in the sky are stars where the plane of their orbit is in the same plane as our line of sight, so that one star passes in front of the other. These are called eclipsing binary stars. We have, let's say, a large star and a small star. We can imagine that the light of the two stars comes along constant, then there's a little eclipse, and then it goes along constant, then there's a big eclipse, and then and this goes on periodically.
The very fact that an eclipse is occurring means that we know we're looking at it from the side. We know the inclination. We know that the Doppler motion is exactly the same as the real motion. In that case, only in that case, we can determine the actual masses involved.
But eclipsing binaries told us more than just the masses of the two stars. They also told us their actual sizes.
Now, with our spectrograph, we can determine how fast a star is moving. So we know in any units like miles per second or kilometers per second, how fast the star is moving in its orbit. As a star eclipses the other one, we see the light from both of them, and then suddenly there's a dip in light as one covers up the other one. And there's a diminished amount of light until this eclipse passes, and then we go back to the original amount of light. The width of the eclipse, the time it takes for the eclipse to occur, multiplied by the speed, will tell us the dimensions involved, the diameter of the star.
Once we began to measure the masses and diameters of stars using various types of binary star systems, we began to become aware of the range of possible values for these characteristics of stars. For mass, for example, stars have been seen as low as 1/10 the mass of the Sun. And there are other stars which are perhaps 50 times more massive than the Sun. Diameters turned out to have an even bigger range. We know of some stars 1,000 times larger than the Sun, the so-called giant stars. If you put one of these where the Sun is, it would engulf all the planets out to Saturn, swallowing up most of the solar system. And then there are some stars which are as little as 100 times smaller than the Sun in diameter. This is about the size of the Earth.
After measuring the masses of stars, naturally one wants to play around to see if there's any correlation with some other parameter that goes with the stars. And so it's natural to plot the masses of stars, let's say, against their color, against their brightness. And astronomers noticed that if they plotted the mass of star against its brightness, there was a almost linear relation. And this holds for stars that we call main sequence stars, the ordinary run of stars.
The mass-luminosity relation is really the key to understanding how stars work. If you understand how that works, then stars are very simple beasts. The mass-luminosity relation is an observational fact. We observe that massive stars, stars that contain a lot of matter, produce a lot of energy, and we say they're luminous. We observe that stars that have little mass have low luminosities. So there's a relationship between the mass of a star and its luminosity. That's an observational fact.
So at last the calculations and observations converged on this single relationship. The more massive a star is, the more brightly it shines. In attempting to explain this most fundamental relationship, we would build all future understanding of how stars work, why some outshine others, and how they're born, live, and eventually die.
For longer than there have been people, the same countless array of stars has filled the sky. It's little wonder that for most of our history we believed the stars to be fixed and eternal. But as we know, appearances can be deceiving. We've come to learn that the stars have finite lives, and the heavens continuously form and give birth to new stars to enlighten the night sky.
Until recently, relatively recently, meaning of course about 10 years ago in astronomy, most of what we knew about very early star formation was theoretical. Now, because we can study the way the gas behaves that condenses to form stars, we can actually see if these theories are true.
On the one hand, we know that stars have formed, and we know that stars are held together by gravity. So somewhere between these big structures in space and now, or at least when there's a star, gravity takes over and makes the whole thing contract, usually in creating a cluster of stars. But there are some severe problems with that when we actually get down to the nitty-gritty.
Under the veil of darkness, the sky shows no sign of the complex nature of star formation. But it's here, in the darkest parts of the heavens, that the story of stellar birth begins.
Hundreds of years ago, quite literally, when some astronomers noticed that in some directions, when they looked through telescopes, there were these very dark regions between the stars. And the most famous observer of the very early dark regions was William Herschel, who called them vacancies in the heavens, or holes in the heavens. But it wasn't until Edward Barnard, who was born in Nashville back in 1857, when he became a professional astronomer, he started photographing the heavens with a camera mounted to a telescope. And he used the first photographs of the dark holes between the stars. And he was very puzzled by them, but he had learned from Herschel's book that these were holes in the heavens. But if they are holes in the heavens, there's a very serious problem implied, because if there's a tunnel between the stars, then, and you see lots of them around you, all those tunnels must be pointed at the Earth. And some astronomers pointed out that that could not be correct. There couldn't be holes in the heavens. There had to be something stopping the starlight.
So it isn't an absence of stars, it's our inability to see through it's like having a dark curtain in front of the stars. It's our inability to see the stars that are there. This absorbing material is very close to our solar system, and so we can't see the stars that lie behind it.
We have come to realize that these are certainly not holes. In fact, they're among the most interesting regions, in my viewpoint, within the Milky Way, because they're not empty. They're very full of dust and of gas, and probably they're the nurseries where the youngest stars are forming.
Once astronomers realized these were not holes in the heavens, they began to discover what this interstellar medium actually was.
The interstellar medium is, as the name suggests, the description of the material between stars. It's interstellar. It's made up of small particles of dust that often come from the envelopes of dying stars, and also from gas, which is of course found throughout the galaxy and throughout the universe.
The gaseous component of the ISM is predominantly hydrogen, and we have trace elements of the other helium and the heavier elements, but by and large we're talking about a lot of hydrogen out there.
we can detect the gas in the interstellar medium directly because we can observe in slightly denser regions the emission from the 21 centimeter line of neutral hydrogen. And this, of course, is the predominant constituent of the interstellar medium. So we can point radio telescopes tuned to 21 centimeters in the direction of where we believe there are denser regions, shall we say, concentrations of interstellar medium gas, and we can map it out by mapping out where we see this line of 21 centimeter hydrogen.
The gaseous component of the interstellar medium ranges in density from the inner cloud medium, which is not very dense and typically 1 atom per cubic centimeter, to the much more dense regions in molecular clouds where you have gas and dust mixed. To give you a comparison, the 1 atom per cubic centimeter is about 10 to the 19 times less dense than what we have at Earth's atmosphere.
Because there's a great deal of gas and dust, a great many things can happen to it. Therefore, if the light from a young star, which is embedded in these enormous clouds of gas and dust, impinges, the radiation impinges on these dense clouds of hydrogen, in fact, it ionizes them, and as a result, it produces what is called an H2 region, and that's what we see, for example, in the direction of Orion, when we see the glowing clouds of gas and dust.
The dust component of the interstellar medium by volume is actually quite small. I guess we'd say about 1% of the mass is locked up in the dust component. But this is still a very important component because it reveals so much of the chemistry that is occurring.
The dust is more like the graphite in your pencils or the silicate that you might find on the beach, gritty stuff. It's nothing that you would call the dust that you sweep off your counters. We can tell this because if we look at the radiation from this dust itself at various wavelengths, we can see characteristic patterns that result from the fact that these silicates or graphite particles are actually known to be the constituents of the dust.
The dust has two properties. One, that it makes, if it's very thick, it can make stars behind it invisible. If it's thinly distributed, it only partially obscures the stars, and it does what we call redden them. It makes them look fainter, and it makes them look redder, so that we tend to think that these stars must be cooler because they're redder, but in fact the scattering by the dust particles causes the reddening.
It's the same as you experience when you watch a sunset on a clear day. As it approaches the horizon, it gets redder and redder. That is because the light from the sun is actually being scattered off particles in the atmosphere. The blue light bounces off the particles, the dust particles. The red light comes through to your eyes. So the sun looks redder than it normally does.
The particles of dust that are doing the obscuration are very small. They are so small that you could think of them in terms of the particles in cigarette smoke. They are in such abundance that when they're all lined up between us and the star that they're obscuring, they will absorb a lot of the light from the star, and we can infer their presence by this absorption.
Dust can sometimes be seen as blue reflection nebulae, reflecting the light of nearby stars. Such dust plays a key role in changing the composition of the interstellar medium.
We now know that molecules form because of the presence of dust in interstellar space. Dust is a catalyst on which two hydrogen atoms can come together and form a molecule, and from molecular hydrogen all sorts of other chemical reactions can take place, producing other molecules.
For a long time, the existence of molecules in space was doubted because of the harsh environment. It seemed unlikely that they could exist. We now know that they are definitely present because we see such clear indications through the radio observations and the near-infrared now. There's no longer any doubt that there are molecules in space.
These molecules there are at least 80 species that have already been identified. A large fraction of them contain carbon, which is very important because carbon is the basis of life. It's what we call organic chemistry. Human life is based on organic chemistry. All life on Earth is based on organic chemistry. Now we find lots of these molecules between the stars.
While the voids of space contain far more than astronomers once imagined, the dust, gas, and molecules that make up the interstellar medium hold even deeper, more marvelous secrets. It's not by coincidence that these vast interstellar clouds contain the very same elements as young stars. For astronomers have learned that in the womb of interstellar matter, stars are born.
I think the most important and interesting problem is how do you actually get from interstellar matter to a star? We know that sometime before the star forms you have a collapsing cloud, but it's not obvious how you get from interstellar matter, which is highly filamentary. In fact, I don't even think there are too many real clouds in this sort of general stage of the interstellar medium. How do you get from filaments to stars?
The birth of stars takes place in dark interstellar clouds that are shielded from the light of other stars and from galactic cosmic rays, agents which might heat the cloud and prevent it from beginning collapse to form gravitationally bound stars. So in some ways, the life of a star begins in darkness.
The requirement for star formation to occur seems to be a certain density and as well as the composition that's available. Just any dark cloud may not be able to form stars because perhaps it's not dense enough or material hasn't coalesced into the proper amount that is required for star formation to occur.
The material that makes these vast clouds, when you estimate how much matter they contain and you can see how fast they're moving, you can actually do a simple mathematical equation which relates the force of gravity pulling inwards and the motion blowing apart, and you find out that none of those structures have enough mass to form stars.
Stars, in fact, could form from any cloud of gas and dust as long as a certain few conditions were met. And these conditions are that there be clumps that are cold and that are dense, and that some other event will trigger these clumps to become more and more dense and to condense out. Star formation is generally thought to be triggered by some kind of external event. At least the formation of massive stars appear to be, and that's if you study groups of very large stars called OB associations. These appear to form either as the result of perhaps excessive pressure because of the passage of a shock wave after a supernova explosion, or when something called a density wave actually passes through the whole of our galaxy, causing star formation to occur not just in one place, but in a whole arm of a galaxy.
When a unit of molecular cloud material begins to collapse, following kinds of events happen, we think. The parts of that material which aren't spinning very rapidly collapse to form the seed of a new star. The star begins to collapse, deriving most of its energy from release of gravitational potential energy. Gravitational potential energy is turned into heat and eventually the luminosity which we observe at optical and at infrared wavelengths. Eventually, the star collapses to a point where the central temperature at the very center of the star, reaches a point which is high enough to begin nuclear burning. That is, in some cases, taking 4 hydrogen atoms and turning them into a helium atom with a consequent release of energy. And it's at that point when the star initiates hydrogen burning, when it becomes a stable, non-contracting main sequence star.
and we've been exploring the regions and nearby molecular clouds in which these stars can form, and see if we can determine whether stars form as individual stars or whether they form in small groups or even in large clusters. And recently we have found, by mapping a cloud just south of the Orion Nebula, that most of these stars form in small families together in groups on the order of 10 to 50 stars. And occasionally there's a larger cluster on the order of 100 or 200 stars will form, but most of the stars are formed in these smaller groups that just slowly escape from the place where they were born.
The Orion Nebula, the entire Orion region, provides a wonderful grounds for studying star formation that is, in a sense, in our own backyard. Because it's so close, 500 light years away, we can see details ongoing in the regions of star formation in Orion that we can only guess at in regions that are much further away.
The Orion constellation is supposedly a hunter. It has 3 lines to form a belt, and hanging from that belt is a dagger, 3 stars forming the dagger, and the middle one is the Great Nebula in Orion. And in that nebula is a cluster of stars, very young, less than 1 million years old, that is still in the gas cloud in which it was formed, and there are still stars being formed in that cluster. That's a young cluster. In the process of these stars circulating around in a sort of random pattern throughout this cluster, they pick up companions in a strictly gravitational way, just like Newton would expect. 2 stars come close together, and perhaps they form a double star system. At first, this is a very random thing. A star will pick up whatever happens to be close by to it as a companion. But these double stars, which tend to be temporary as long as the stars are in clusters, are sort of like Hollywood marriages in the sense they come and go. A star will pick up a companion, and those 2 stars will revolve around each other for a certain length of time. But then the 3rd star comes along, and like a love triangle, it may break up this happy marriage and take the companion away. And then the primary star will look around and try to find another one. It doesn't consciously do this, but just through gravitation, another companion will come and it'll pick that up. So if you follow these motions through many, many cycles, the stars pick up companions and they get rid of them, and pick up other companions and get rid of them.
Whether they will live alone or in pairs, newly forming stars are nurtured in the celestial womb until they reach the main sequence stage of their lives. During this time of development, these protostars show no visible signs of existence. Still, we know they're there. Enshrouded in the darkness of interstellar dust, stars slowly form, hidden from the human eye. It's only in recent years that astronomers have found the means to detect their presence.
We can't see dust with the naked eye. We can only see black patches, for example, in the middle of the Milky Way, which often you can see stretching across the sky, especially in August and September and October.
In the optical regions, the dust is just too dense and the light does not escape from the clouds. And so in order to look at the earliest stages of star formation, we have to look in the light in the near infrared, in regions where the instruments are just now becoming available to allow us to do this.
So when we talk about the infrared part of the spectrum, we're talking about wavelengths of light which are 2 to 3 times that of visible light, and photons of energy 2 to 3 times lower and lower than that, and a longer wavelength than that.
In looking at the different regions of the infrared, we're actually sampling the different temperatures that these objects are at. And if you want to study the very coldest regions of star formation, you'd want to look in the far infrared or the longer wavelengths. And if you're looking In the near-infrared, you're seeing the hotter, warmer objects. They're still quite cold by comparison to evolved stars, but they are warmer than these very cold regions that would show up in the far-infrared.
The protostar emits at ultraviolet wavelengths. This emission is absorbed by dust grains, and when it's re-radiated by these relatively cool dust grains, it emerges at infrared wavelengths. And so it's almost a signpost of what's happening within the cloud in the protostellar region. It's not exactly a direct measurement, but from the intensity of the re-radiated emission, we can find out a great many of the properties, how massive the protostar is, what kind of a star it's likely to be. These can all be discerned from the re-radiated information.
Infrared astronomers work at telescopes much like the optical astronomers. We have a very special telescope, and that is the Kuiper Airborne Observatory. It is a telescope built into an airplane, so it affords us the ability to get up above most of the Earth's atmosphere, which is critical for the infrared astronomer. Typically, before a flight series, we will sit down in front of the computer and devise a flight plan that optimizes those objects that are most important to our scientific program. We'll be starting out where it says leg 1, leaving from Moffett Field. We'll be flying north, and then we have a long leg as we go down south. This is one of my main target objects.
Okay.
And then we move over this way, and we have 2 more of the main target objects. And in between, we have standard stars that we'll be looking at.
And this gives you the direction of the airplane. The telescope is always pointed to the left from the airplane. So
we typically have a team of maybe 3 or 4 people that are associated just with the instrument, and then the scientific principal investigator and any other support personnel that we might need.
We're going to have a lot of people, so try and keep the chatter to a minimum on the interphone so that the science can take priority and get done.
The way an observing flight typically runs is that you have a combination of people that come to it with their own areas of expertise. We will have the instrument developer and the people who run that instrument present, and we will have the computer operators, the telescope operators, and the scientific investigator who will guide the science that is being done on that flight. It is a matter of complete teamwork in order for the data to be obtained, and it could not work without the expertise of each one of those individuals. Inside the cavity of the Kuiper Airborne Observatory is a 1-meter glass telescope, and it is a Cassegrain telescope. The size of it was very carefully constrained to fit within those dimensions. During the flight, we're able to see the data that's being collected, and while it's not really possible to analyze it thoroughly while you're in flight, you're certainly able to see whether or not you're getting the quality of data that you expected. The types of experiments that we do from the Kuiper range from the near-infrared to the far-infrared, and it's dependent on the type of instrument that is available for the particular wavelength region of interest. These wavelength regions are regions that we cannot look at from the ground. So there is complementary information to be gained from the near and far-infrared. In the near-infrared, you would look at the dust surrounding a very young star, and in the far-infrared, you might look at a neighboring region that is less evolved.
Infrared technology enables us to peer through the veil of obscuring dust. Within what appears as empty space, infrared wavelengths reveal the warm glow of stars in the earliest stages of their lives, a condition that does not last.
When a star first forms, it's enshrouded in a cloud, a molecular cloud, and then at some point it manages to clear the cloud and we see the star for the first time. And if it's a solar-type star, we call it a T-Tauri star. The significance of that, of course, is that it's our first direct view of star formation in progress. The winds in T-Tauri stars are one of the most interesting features of these stars. We see evidence for the winds almost immediately. People can see that the molecular cloud in which the T-Tauri star is formed starts to flow away from the site of formation long before you can see the star itself. And in fact, we see evidence that these outflows go on all during the time that the star is kind of buried in the cloud. So they probably begin maybe 100,000 years or less after the actual collapse to the star begins.
When the star first forms, it probably pulls in magnetic field from the interstellar clouds. So it may begin with a field, but then this field would dissipate and it has to generate its own field. So we think that the process of the star generating its own field, which we think is necessary for the wind, begins when the star first begins to burn nuclear material. This is not the hydrogen burning in the star which takes place on the main sequence, but it burns what we call heavy water or deuterium. And this can occur at a much lower temperature, and it occurs within the first few 100,000 years that the star is formed.
The other kinds of phenomena that one typically talks about in looking at star-forming complexes are so-called Herbig-Aurel objects. These are manifestations of interactions between the winds which almost must accompany stellar birth in order that stars not spin up to a critical velocity so that they lose material at their equators faster than they can gain material. The winds that are emanating from these stars interact with the interstellar medium, shocking the interstellar medium, heating the interstellar medium, and producing a unique emission line spectrum which signals the birth process in an indirect way.
It was some of these Herbig-Aurel objects which led us first to find some of these stars buried deep within the cloud, because we saw these objects radiating in just very high excitation emission lines, and we had not been able to find the sources of their excitation.
I think that was probably one of the most exciting moments, at least that I can remember, back in the mid-70s when we first turned the infrared detectors toward the Herbig-Aurel objects and tried to find the exciting stars. And I think if I had to imagine, we knew that there was something having to do with stellar birth, as did Herbig and Aurel before us. And so it's sort of a combination of observations of stars and the observation of nearby star-forming complexes that are going to give us some sort of deeper understanding of the star formation process as it's occurred over the lifetime of the universe.
It's been a journey of 1 million years or more. From nothing more than the gas and dust of the interstellar medium, the star has been formed by pressure and gravity and born into the maternal arms of the galaxy.